In this video, we are going to go through the basics of infrared spectroscopy. And what infrared spectroscopy is a lab technique that allows us to determine the functional groups. So this is just going to help us determine functional groups. Now, basically, we shine infrared light at a sample, and it's going to cause different vibrations or stretching or rocking and so forth of our bonds and our atoms. And depending on what rotations and stretching happens, that will produce a specific graph. And functional groups tend to have specific characteristics that they absorb as far as light. So what we have is a graph that looks like this. It looks complicated at first, but we'll be able to identify certain peaks as we go along. So looking here, how I'm going to break this apart is around maybe, I don't know, and maybe that's a bit low, maybe 1400 wave numbers, and we'll talk about what that is. This is going to be called the fingerprint region. And this is difficult to determine groups here. Okay, so we typically will not look in the fingerprint region. That's not to say never, and it's typically single bonds that occur in this region. Okay, now we're going to go from 1500 to 2000 wave numbers. Wave numbers are just the type of light. So you can measure light in nanometers, you can measure light in hertz and its frequency. Wave numbers is just a conversion. You'd never be tested on it, at least in my organic chemistry class. But between 1500 and 2000, this is going to be our double bond region. And then from 2000 to 2500, this is going to be our triple bond region. And between 2500 and 3000, this is typically a CH bond region. And then from 3000 to 4000 is typically our OHs or our NHs. We can have some couple other things there, but typically that is how this is going to be organized. Now, stick with me. We're going to draw some things. I think you should have maybe 5 sheets of paper. I know I added 5 sheets of paper here that I'm going to write on. I'm going to draw all the different functional groups on a graph, and that is going to help us kind of get used to how to read these graphs, because when you first see these infrared spectroscopy graphs, it's only normal to say, wow, those look really confusing and difficult. Okay, so what you have on the back of your periodic table is you have these IR values. Okay, so this is just a Mr. Payne chart that I've made that you don't need to memorize the numbers that we're going to start writing. So here's what we're going to do. We're going to start on our pieces of paper. So make sure you have 5 sheets of paper, whether it's lined paper or copy paper. We're going to start with alkanes. Alkanes, we're going to draw a graph, and how our graph works is our y-axis is percent transmittance. Our x-axis is going to be wave number, and wave number is typically measured in inverse centimeters. And we're going to go from 4,000 to 3,000 to 2,000 to 1,500 and then to 1,000. Okay, that's how these are most likely represented. And then we're going to have, I always like to draw a line for our fingerprint region. You don't have to, but just for me, it's kind of nice. So an alkane is going to be something generic, like maybe something like this. And we could have R groups, keep going, but we're just focusing on alkanes. So in the fingerprint region, we might get some peaks and they might look like that. Not important to try to distinguish those. Because alkanes are just single bonds, we're going to skip over the double bond section and then skip over the triple bond section. But typically at around, I don't know, 2900, if you read your chart here, it might have the specific number range. These are all very rough, okay? So there's going to be plenty of variation and exceptions. Just these are guidelines, not, set in stone numbers. At around 2900 to 3000, you'll see some squiggles, and it might look like this. And this is what we call alkane stuff. I don't know if that's a very scientific term, but that's what I call it. And it's basically CH. And notice how I had single bond C, then H. So that does make a difference. That's just alkane stuff. Okay, no big deal. This is just alkanes. Typically, we're not worried about alkanes just because most organic compounds are going to have alkanes present. Okay, my second graph. Okay, let's take a second and draw it. And we're going to get 4,000, 3,000, 2,000, 1,500, and then 1,000. We are going to do alkenes next. So we'll draw our fingerprint region. We are probably going to have some sort of peaks going on there, and they might even be big peaks too. It's not really a big deal. They're just hard to distinguish, and if you continue on in organic chemistry, you'll definitely learn how to read the fingerprint region. So with alkenes, we've got double bonds, so we might get something that looks like this. So what I'm going to get is probably a peak that looks like this. I'm probably going to have some alkane stuff, and it might be kind of squiggly. And it might look like this. So this is my CH, and then this guy at about 1600-ish is my CC double bond. Okay, so we start to see that when we have specific functional groups, we get these unique peaks. Okay, I'm going to copy this because I think it's kind of nice since I have the ability with this iPad. We're going to change this. Now we're going to have, instead of alkenes, I'm on the next page, we're going to do alkynes. And alkane stuff is still going to exist. It might get shifted a little bit down, and that's not a big deal. And this would be a CC triple. The thing that's going to be different here is I've got a triple bond. And so triple bonds, let me just erase this part. I'm making it more complicated than it needs to be. Okay, triple bonds are going to happen between 2,000 and 3,000. If we scroll back up, specifically, alkynes, that triple bond occurs between 21 and 2,200. So I just want to make sure that it's reasonably within that range. And they tend to be kind of pointy. That's not always the case. That's just what I've noticed. I don't even know if other people have noticed that. That's what I've noticed. Now, we're going to get alkane stuff. And here's one thing that's going to be different is if we have a terminal alkyne, we're also going to get a peak here for this bond. This is only for terminal alkynes. Okay, so if that triple bond is in the middle of your structure, that goes away. Okay, so after alkynes, I want to make sure I get all of them. I'm going to do alcohols. And an alcohol group, hopefully you remember, is going to be some sort of carbon group and then OH. So Alcohol groups you're going to really like when you see them because they're probably the easiest one to identify because they have a parabolic shape. So between like 4,000 and 3,000, maybe close to like, I don't know, and I've got the number. It's hard for me to know the exact number that's on here. In alcohol, 32 to 3,700. So that's the general guideline, but it's a very big range. We're going to get an OH peak, and it just is very parabolic in what it looks like, and it's very distinguishable. We're going to get alkane stuff, so alkane stuff might be there. Nothing in the triple bond or double bond region if we just have an OH. Now, one thing we'll get at around 12 to 1,300 is we'll typically get a CO single bond. And you say, well, that's not hard to see, but what it'll probably be disguised in is a bunch of other noise. Okay, so you can see how maybe that single bond, it's there, but it's going to be hard to actually pinpoint it. Okay, now let's do ketones. We got 4,000, 3,000, 2,000, 1,500, and 1,000. Ketones are going to be specifically RCR. So the distinguishing characteristic is this CO double bond. Now, double bonds occur between 1,500 and 2,000. 1,600 is CC double. 1,700 is CO double. So that's kind of nice. That just kind of rolls off the tongue once you see this a couple times, so that'll be nice. So I want to make sure I have this at about 1,700-ish. We're going to always have some alkane stuff, so and then we'll have some squigglies in my fingerprint region, and they might be big or small. It doesn't really matter for what we need. Okay, after ketones, let's do aldehydes. Aldehydes are very nice. I like aldehydes. So I'm going to draw my chart. And aldehydes, you've got them in your notes, but they're going to be R, C, and then H. Okay, so we're going to have, and maybe I move that a little bit to 1,700-ish. We're going to have C double O, 1,700-ish. We might have some squigglies in the fingerprint region, and I got very sloppy with how I wrote those. Here's what we're also going to have, is we're going to have alkane stuff. But aldehydes, I want you to remember aldehydes have fangs. And those fangs occur if you scroll up a few pages with what's on your periodic table at 28 and 2,700-ish. So what those will typically look like is you'll have one peak and then maybe another peak. And these are going to be your aldehyde fangs. They're very distinguishable. Here's the issue, though. I'm going to scroll back up to vanillin, which was on a page up here. We've got an aldehyde. This is a C. We've got an aldehyde. Notice that on this page, we've got alkane stuff. And I'm going to draw in red. Our aldehyde fangs, they're there, but the second fang gets kind of covered with alkane stuff. So sometimes it bleeds in to alkane stuff. So we get something that looks like that. Okay, you'll like aldehydes just because they're kind of easy to identify. Okay, let's see if I can get some others. Let's do ethers. Hopefully at this point you are really good at drawing this graph. And for ethers, those are typically anesthetics, but they don't have to be. We have ROR. So we're going to get a very boring graph because we're mainly just single bonds. So we'll have alkane stuff. We'll skip over the triple bond region. We'll skip over the double bond region. We will typically see, not always, a CO single bond at around 12 to 1300. But it's going to probably have some noise that makes it difficult to see the rest of it. Okay? Ether is very boring. Okay, carboxylic acids. Okay, so you got to know your functional groups. You may not know them just yet because the way things are, you're just kind of learning them right now. But that's going to be RCOH, or you might even write it OH like this, and then double bond O. So we can start to plug in some things that we know. We might get at 1200 a CO single bond. Now, I've said it multiple times in this video, but it's going to be hard to actually find that because it's in the fingerprint region, which typically has a lot of noise. Now we have a CO double bond. So that happens at around 1700. We are going to have alkane stuff right below 3000. Skip over the triple bond region. Then we're going to have alcohol. And what a lot of people do, don't write this, is they'll say, oh, alcohol. However, a carboxylic acid, if it were just an alcohol, we call it that. It's actually a carboxylic acid. It behaves differently. It has different chemistry. And we'll learn about that with these two O's being so close together. Resonance is possible and lots of other things that we will explore. So I always say we are going to get a squiggly, deformed alcohol. So if you remember me saying an alcohol group is very parabolic in nature. Well, let's take that parabola and make it squiggly and deformed, and that's probably what a carboxylic acid alcohol is going to look like. So it'll still have the general shape, but it's going to be deformed. Okay. Okay, I want to add another page. I miscounted, so I'm going to delete this. Actually, you know what I can do to be smart? So go to another page. We've got two more, and then we're done with all the types of graphs here. So just give me a second. Let's do an amine group. We are still going to have our fingerprint region. An amine group is an NH group. Let's say we have an NH2 group. So it looks like this. Because this nitrogen is bonded to one carbon, one R group, this is going to be called a primary amine. We are probably around 12 to 1300. Also going to have a CN. It'll probably be hidden. We're not going to worry so much about it. We're going to skip over our double bond, skip over our triple bond section. We will have alkane stuff as we do. And I'm going to copy and paste this actually because I want to show you how it's different. So take a second and draw your last one. It's going to look exactly the same as this right now, but I'm going to change it one thing. So I'm just going to draw that below there. Instead of it being primary, I'm going to change it to secondary. And a secondary carbon, it's not NH2, but it's only NH, so we have two R groups. And here's where things get different. Is in the OH section, that's also the NH section. Okay. Now we're going to get, it's not going to look so broad and parabolic, but we're going to get peaks. Here we have two H's. So we're going to get two NH peaks. So this is NH. When we do that for secondary, if we look, we've only got one H. So we will just have one peak. And that's it for the functional groups. You're going to get better at this when you do some practice problems. We've got 5 of them coming up, and then we'll be done with this video. But stick with it, and I promise it will get easier. So let's look here. We have isomers here. Isomers, the prefix iso means same, and so this is going to be a compound that has the same formula, but it's bonded in a different manner. So you can think of some things that maybe you did in regular chemistry. If you've talked about mass spectrometry, we could figure out what these are and we could figure out their molar masses, but we actually wouldn't be able to tell them apart because they have the same formula and therefore they have the same molar mass. So this is a case where infrared spectroscopy can help us out in a very unique situation. So what I want you to do is I want you to pause the video if you would and look at cyclobutanol, butanone, ethyl vinyl ether, 2-methyl, 2-propane, 1-ol, and then 2-methyl-propanol. And I want you to figure out what groups, what functional groups are unique to them. Okay, so pause the video and I'll write them here. Cyclobutanol has an alcohol group. Butanone has a C-double-O. Ethyl vinyl ether has a C-double-C. And maybe we can find that's going to be a single bond in the fingerprint region, so we'll see. And then if we look at propanol, we have C-double-C and OH. And then propanol, propanol, the last one, we have C-double-O and aldehyde. Okay, so I'm going to call this compound 1, compound 2, compound 3, compound 4, compound 5. And what we're going to do is we are going to look here at this graph. And let's look at our distinguishing characteristics. So here, 1400 to 1500-ish, that marks our fingerprint region. We don't really care about that so much. Here's what I see, is I see something happening here. This definitely is around 1700-ish, so this is C-double-O. I see alkane stuff. What I also see is maybe fangs, so I'm going to just write fangs, question mark. So for sure we have a C-double-O. So the only two that could possibly be are number 2 and 5. I don't need to narrow it down to which one it for sure is right now. I'm just going to keep moving, okay? So I've narrowed it down to what maybe it is. I have a good idea, but I want to prove it. Okay, we go to the next page, same 5 compounds. Here, I'm going to mark my fingerprint region. Notice I do it very rough because it's just kind of an eyeball here. I get another 1700-ish. So automatically that COO only occurs in 2 and 5. So the difference between 2 and 5, what we said up here, is that 5 has an aldehyde, and we know aldehyde is fangs. So I want to see which one maybe has fangs. If I look at letter B here, this guy has no fangs. So automatically, this is number 2, and then this guy is number 5. Those were fangs, okay? Remember what I said earlier in the video, sometimes they get hidden. Okay, so we've gotten 2 of them down. Let's keep moving. On C, hopefully when you see this, this is for sure an alcohol group. Very parabolic, very straightforward. So the letters that have alcohol are 1 and 4. The only difference between 1 and 4 is that 4 has this double bond. So what I want to do is I want to say, okay, CC double occurs at 1600. I don't think this is probably not CC double. Okay, CC double tends to be very distinctive, and that's kind of like noise. Okay, but we'll just narrow it down between 1 and 4 right now. We don't have to make a decision. When we get to D, we do have an OH, absolutely. So again, we're between 1 and 4. 4 has that double bond, so let's see if we get a good double bond here. That's pretty close to 1600. I would say that that's a better choice for the CC double bond. So this guy is 4, and then that leaves this guy as 1. Now, let's prove why E is 5. Or not 5, excuse me, which one have we not done? Ethyl vinyl ether, 3. We should have a CC double, absolutely. We have something happening around 1600. And then here, even though it's kind of hard to tell, look at all the noise throughout here, I think this peak, the one right here, is a CO single. So this is compound 3.